Good morning, student. In this session, we will take the fluid property, that is viscosity. It is also known as dynamic viscosity or coefficient of viscosity or absolute viscosity. So it is defined as the property of fluid by virtue of which it offers the resistance to flow. I am keeping two fluids. One is honey and another is water. So just see, water is flowing at faster rate. So we have seen that if two fluids are kept on this inclined plane, then one fluid is flowing at a faster rate than the another fluid. In our case, we have seen that the water is flowing at a faster rate than the honey. It means that the honey possesses higher viscosity than the water. So it is defined as the property of fluid by virtue of which it offers the resistance to flow. Suppose fluid is flowing on this surface. This is plane surface. We will assume that it is flowing in the form of different layers. So viscosity may be defined as the property of fluid by virtue of which it offers the resistance of one layer to the adjacent layer under the action of shear stress. Let's see the definition. Dynamic viscosity or coefficient of viscosity or absolute viscosity, it is defined as the property of fluid by virtue of which the fluid offers the resistance to the deformation under the action of shear stress, or it is the property of fluid which offers the resistance to the movement of one layer, because the flow that we are considering in the form of layer. So it is the property of fluid which offers the resistance to the movement of one layer of fluid over the adjacent layer of the fluid. Suppose the fluid is flowing on this surface from left to right in this direction. The lower layer, suppose this is a lower layer, is moving with velocity u at distance y. Then at a distance dy, the velocity of top layer will be u plus du. Suppose fluid is flowing on this surface with velocity u in the form of layers, different layers. We will consider one layer at a distance y. Suppose the velocity is u, and then we consider a layer, upper layer at a distance dy. In that case, the velocity of top layer will be u plus du. We observe that the top layer has the maximum velocity and the lower level has somewhat less velocity. That is due to the friction offered by the layer, and because it has to overcome the shear stresses, and then the adjacent layer or the lower layer will possess still lower velocity. So gradually the velocity reduces, and at the end the velocity goes zero at the surface. And if we join all these points, gradually velocity reduces due to the friction, or because it has to overcome the shear stresses offered by the plane layer. So if we join these all points, we will get the velocity profile. When two layers of a fluid a distance dy apart move one over the another at a different velocities, say u and u plus du, two layers are there. One is moving with velocity u and another is moving with velocity u plus du. The velocity together with relative velocity causes a shear stress acting between the fluid layers. The top layer causes a shear stress on the adjacent lower layer, while the lower layer causes a shear stress on the adjacent top layer. This shear stress is proportional to the rate of change of velocity with respect to y. It is defined as symbol tau. Suppose it is flowing in the form of layers. This is top layer and this is lower layer. Then top layer moves with higher velocities and the lower layer will flow with less velocity. As the lower layer offers the resistance to flow. The top layer is moving with higher velocity and lower layer is move with lower velocity, and this adjacent layer to the lower layer will move still with lower velocity. In this way, the velocity here at the top is maximum and gradually reduces to 0. That is due to the shear stresses offered between the layers. Now, at distance y, if layer has the velocity u and just above this layer at a distance dy, the layer will have the velocity u plus du. So du is the increment in the velocity. Now the amount of shear stress produced here will be proportional to the velocity gradient, that is du upon dy. Du upon dy is the strain, or it is known as velocity gradient. So shear stress is proportional to du upon dy. So removing the sign of proportionality, we introduce a constant mu. So tau is equal to mu into du upon dy, where mu is known as coefficient of dynamic viscosity, and we can write by mathematical transformation the mu is equal to tau upon du upon dy, where du upon dy represents the rate of shear strain. This is tau is the shear stress and du upon dy is the shear strain. So we can define the viscosity as the amount of shear stress required to produce unit rate of angular deformation, or thus the viscosity is also defined as the shear stress required to produce unit rate of shear strain. Here, if this is equal to du upon, if here just see, if du upon this quantity is 1, this is 1, then tau is equal to mu. So the viscosity, coefficient of viscosity or viscosity may be defined as amount of shear stress to produce unit rate of angular deformation.